Hi everyone, we are Team 1 and our project title is using head orientation to improve BCI-based quadcopter. The presentation will proceed in the following order. The way to control a robot based on human intent in real time are diverse. A popular method is joystick manipulation, but voice or gestures can be used as input commands. These methods have in common that they involve body movements. So, what way can be used if the operator cannot move his or her body at will? Several studies have suggested BCI as a counter input for this situation. BCI is a computer-based system that acquires, analyzes, and translates brain signals into output commands in real time. The robot control using BCI is as follows. First, record brain signals with an easy cap. Second, process the data by computer and send the resulting command to the robot. Then the robot does the act as the operator intended, and return feedback moves the operator as they see the robot. This paper, quadcopter control in three-dimensional space using a non-invasive motor imagery-based brain-computer interface, is one of the studies about controlling a robot with BCI.
Its goal is to control a robotic quadcopter in a 3D physical space by means of a motor imagery EEG BCI. It is the first paper demonstrating the ability to control a flying robot in 3D physical space using non-invasive scalp-recorded EEG in humans. Because it is the basis of the following of BCI drone studies, we chose it as a base paper for our project. The motor imaginations corresponding to each control are seen in below drawn figure. Separable control of each dimension was attained by imaging clenching of the left hand for left turns, right hand for right turns, both hands for an increase in altitude, and no hands for a decrease in altitude. The control scenario is performed under the right figure, which is the experimental environment. A target hit was given if the subject successfully explored the quadcopter to pass through the ring, but a ring collision was given if the subject only collided with the ring. If the quadcopter deviated from the boundary of the control space, the trial will end and the subject will be assigned a wall collision. In this experiment, the subjects are required to achieve a lot of target hits without causing a collision within the time limit. However, there are several limitations in this paper. First, MI is an intuitive BCI paradigm, but control system with using it is unstable. In addition, there is a large user workload to rely solely on BCI to control. Finally, there are individual differences in accuracy in controlling only with MI. Therefore, we will try to improve these limitations. Next content is about related works. The first paper suggested that using head and gaze orientation could improve predicting the directional intention. The next paper proposed a multimodal BCI combining motor imagery and steady-state visual evoked potential to achieve stable control of quadcopter in three-dimensional physical space. These multimodal BCIs have proven to have the ability to increase accuracy rate, reduce workload, and improve the performance of BCI-based control system in the real world.
Next up is our replication plan. So we plan to replicate the work in simulation environment. We're planning on using Unity to create simulation environment for controlling a motor imager-based quadcopter. Using a quadcopter asset available in Unity Asset Store will allow us to replicate a drone object, and Brain Vision software will enable us to take brain signals information from the user in a reliable manner. And based on received brain signals, we can infer user intention after a decoding process. In the bottom is the flow of how it's going to work overall. The user will be making an imagination of their body movement. EEG, or the brain signals of the user will be recorded in real time by brain vision device. Receiving the EEG data and the decoding process based on the received EEG data will be done within the Python script. The script will decode the signal to figure out what the user intends to do. Once the decoding process is finished, and we have information about what the user is thinking, we're going to be converting the classification of the user EEG into a command suitable for a drone movement. And this command will be handed over to a simulation program made using Unity to execute the drone movement within the Unity environment according to the received command. And here is our plan for the improvement. We aim to improve the performance of a BCI-based quadcopter by adding extra information that might encode users' intention. While the paper we chose proposed a method that uses only the motor imagery to control the movement of a drone, our proposition is that adding head orientation information of the user on top of EEG information when decoding user intention will help improve the performance of the drone control. This is based on the hypothesis that users' head orientation information will tell us, or at least gives us hint about where they're intending to move. The simulation will be done using a virtual reality device as it allows us to receive head orientation data in real time. We also thought that showing the drone perspective in first-person view in immersive environment could make head orientation more useful when predicting the intended direction to move. So to sum it up, we have two major sources of information. One is the user's brain signal, and the other one is user's head orientation information. And by referring to these two information, we're going to be merging these two and make a better and more accurate decoding result compared to the original paper. Now, this is our tentative plan by week. So for the first week or two, we're going to be spending our time implementing a model and algorithm presented in the original paper. And once that is finished, we're going to be implementing our planned improve method so that we can add head orientation information to better decode users' intention. And once all the implementation process is finished, we're going to be going through some experiments to check if our model is actually better than the original one. And once the experiment is over, we're going to be analyzing our result from the experiment and analyze in a deeper manner. And for the last week of the semester, we're going to be spending time preparing our final presentation. Now that brings us to the end of the presentation. Thank you so much for listening.